Welcome to the Databricks MLOps virtual event. I'm Ben Lorga, and I will be your host for today. We have an exciting lineup for you today. We have a series of short presentations from a diverse set of speakers and industries, so you'll really enjoy hearing about the practice of machine learning in a variety of settings. Today's lineup will include presenters from Databricks, Blue Cross Blue Shield of Illinois, Atlassian, QB, and Outreach.io. We'll also have a panel discussion to cap off the event. For those of you who are not familiar with who Databricks is, our company was founded by the original creators of Apache Spark almost 7 years ago. And our mission is to help data teams solve the world's toughest problems. Lots of people recognize us as the creators and founders of some of the best-of-breed open source technologies, starting with Spark, which was the first unified engine for processing both big data and machine learning, and has become the de facto open source standard in the industry. And more recently, Delta Lake, a storage layer that sits on top of your existing data lakes and brings performance and reliability to your data lakes. MLflow, an open source platform to manage the complete machine learning lifecycle. And Koalas, a new framework that allows to quickly Sparkify Pandas code. So let's get started. Let's jump in. We have a packed agenda for today. Our opening keynote on MLOps and ML platform state of the industry will be delivered by Matei Zaharia, co-founder and chief technology officer at Databricks, and Clemens Mewald, director of product management at Databricks. Matei and Clemens will be followed by Sean Owen, principal solutions architect at Databricks. Sean will be giving a demo on data science and machine learning operations on Databricks using MLflow.
Hi, I'm Matei Zaharia, Chief Technologist at Databricks, and I'm excited to kick off this event by talking about the concept of machine learning platforms, how organizations are building machine learning platforms to automate MLOps, and what are some of the main components involved. So I think everyone's seen stories like this on the difficulty of deploying machine learning. This is a kind of a well-known tweet from the O'Reilly conferences where someone said, "It took me 3 weeks to develop a machine learning model, but it's been 11 months and the model is still not deployed." And there's definitely been a lot of work to make just deploying the models in the first place easier. But it also turns out that after deploying, operating machine learning is also complex. There are a lot of challenges that come up. So for example, monitoring the performance of the model to make sure that it's still working on whatever, application specific objectives you have for it can require a lot of infrastructure. Dealing with data drift when the data is changing and you have to update the model, or when the version of the data, in deployment is different from the version in training is a challenge. And of course, governance and security, tracking what went into it and how to update it over time can also require a lot of work. So what we found at Databricks, working with organizations of all sizes, is that many machine learning teams spend over half their time just maintaining existing models instead of building new ones for new use cases. So it's quite a bit of work, and it means once you put together a team that's doing machine learning and has set up the basic infrastructure, they deploy their first model, they're excited to do something else, but actually they have to spend a lot of time just maintaining it. And so we'd like to make this faster. So let's look into a little bit more detail at why machine learning is hard to operationalize. Overall, from what we've seen, we've identified 3 main reasons. The first one is the dependence on data. So machine learning applications need new data to keep working well, and the data needs to be high quality, and it needs to be consistent, of course, between training time and inference time so that the model can actually generalize and work on the new data. So that means all the challenges of maintaining a data pipeline have to be solved to do MLOps. So that's one set of challenges. Second challenge is that there are a lot of application-specific, maybe subtle ways to evaluate the model's performance. So you often have to build a complex infrastructure for metrics and experiment management and so on as well to see how your model is doing. And that requires a bunch of work. And then the final one is that there are many different teams and systems involved. For example, you might have a data engineering team that uses systems like Apache Spark for their work to provide the data, then a machine learning team that uses systems like TensorFlow or PyTorch, which are quite different, and then finally an application developer who has to actually deploy both the data and ML modeling parts into, say, a set of containers in their data center or a set of edge devices. And the handoff of applications between these teams and the interaction between these can also create challenges. So in response to these challenges, there's been a pattern emerging, which is the concept of machine learning platforms. So a lot of organizations are designing software platforms to manage the ML applications. So you don't just have people using arbitrary tools, but instead you have a way to do both the data preparation and modeling and deployment and monitoring that is consistent and that can be automated. So these are just software platforms that reach from development to production and manage these applications lifecycle. Now, what we found is that most companies that use ML at scale or in production are actually building a platform. It includes not just large, tech companies, but even very small teams that we talk to. They find this concept useful, and they're spending quite a bit of time figuring out how to design it. So some of the best known ML platforms are the ones at large tech companies such as Facebook FB Learner or Google TFX, but there are also quite a few, much smaller scale ones that have been successful, and we've seen this pattern works really well for letting a team be successful with machine learning. So what are the components in a machine learning platform that you should think about when designing one? Now, this is still a pretty new space, and there are a variety of ways to do it. But we've looked at a number of these, and we've identified at least 3 really important components to think about. And these are ones that you should definitely take a look at. So I'll briefly explain these, and then I'll also talk about some existing solutions for them. The first component is data management, both during development and at inference times. You need to think about how you'll transform the data reliably and in the same way for, in both cases. Quality monitoring, so writing jobs or expectations or some way to check whether the data looks correct. Data versioning, perhaps, that's a very useful thing if you have it to make the data reproducible. And there's also this emerging concept that kind of combines these things called feature stores, which is sort of a database of machine learning features that teams can use the same way in development and at scoring time. So there are a number of open source and commercial tools in this space. At Databricks, we developed Delta Lake, an open source versioned data management system on cloud storage, and that can be used to do this. But there are also other tools like Apache Hive, DVC for data versioning, or Feast, which is an open source feature store, and a number of commercial tools as well. This is one component to think about. The next component is model management. So during the development of an application, you'll create many versions of a model, and you'll also be updating it over time or maybe sharing it across teams. So it's important to think about how to package these models, how to review a new model, maybe experiment with it, how to test it, and how to keep track of all these versions. So there's this concept emerging of model registries that allow you to do that. Again, a number of tools cover this space. At Databricks, we develop MLflow, an open source ML platform system that includes a model registry that supports these features. But there are also tools like PyTorch Hub, TensorFlow Hub, and ModelDB that cover some of these tasks in model management. And then the final component is managing your code and deployment. So this spans everything from how to run experiments or training pipelines in a reproducible way to how to run model serving and also how to do monitoring or experiment management where you've deployed different versions. And this is the area with the most tools out there now. So again, systems like MLflow can provide experiment management and packaging of your code, but there are also systems focused on deployment like Kubeflow and Seldon for Kubernetes or Binder for managing Jupyter notebooks, and there are also cloud platforms that cover some of these, such as SageMaker and Azure ML. So I think, when designing an ML platform, these are at least three of the biggest areas to look at and make sure you have a solution for each of them that can work together and can provide what you need. So our approach at Databricks looking at all this is, of course, we want to support organizations doing this, but we found that every team's requirements are different and they also change quickly over time. So, for example, the team might be using R today to do machine learning and then they switch to Python, or they might be using one library and one data source and then switch to another. So we focused on designing general platforms that can tackle the big issues here, like for example a model registry or versioned data storage, and then making them easy to integrate into your own custom workflow using APIs and other ways to plug in. So that's kind of our philosophy. And we provide, three different components that enable this. There's our commercial cloud service, which is a hosted environment for data science and ML. There's MLflow, which is the kind of the core parts of the machine learning platform. So everything to handle experiments, models, workflows, and so on. And that's open source, and you can run it, in any environment. It integrates with, quite a few more things than just Databricks to give you a consistent interface across them. And then there's Delta Lake for versioned storage on top of data lakes that covers quite a few of the data management tasks. So these components can work together as a basis of an ML platform, but it's also quite possible to take these alone or to customize them for whatever you need. So in this webinar, we're going to give you an overview of how we and other organizations are building ML platforms and handling these three main issues that I talked about. And we'll have demos as well as experience from 4 different companies that have built these platforms. So we're going to kick off next with Clemens Mewald, the head of product for data science and ML at Databricks, who's going to explain how we designed these into the Databricks platform. And then we'll also hear from other companies about what they built and see 4 different ways of tackling this.
All right, thank you, Matei, for the overview and the introduction. And with this, I'm going to show you how we're addressing these challenges in Databricks. So let's start with an overview of Databricks as an end-to-end data science and machine learning platform. I'm going to walk you through the different components of this platform that span all the way from data ingestion to building models and deploying them in production. One highlight to mention here is that Databricks is a unified and collaborative platform. So often different personas own different steps in this lifecycle, and on Databricks they can all collaborate to build meaningful solutions for their businesses. Another point to mention is that this platform really provides the best-in-class open source tools that are integrated in an enterprise software offering. Of course, Delta Lake, Spark, and MLflow are all open source. And we also use other open source technologies across the stack to really provide an open platform. So let's start with MLflow, which is really the foundation that pulls together a lot of these components into an end-to-end solution that addresses the MLOps challenges. MLflow consists of several components, and I'm going to introduce each component briefly before I go into depth when I discuss the lifecycle of a machine learning model. So the projects component provides a way to package up your code and make it reproducible. So if you use the MLflow projects abstraction for your code, you can use the MLflow CLI to run them locally on your laptop or execute the same code remotely on Databricks. The models component provides a standardized format that packages up ML models trained in any ML framework and abstracts away the idiosyncrasies of those frameworks for deployment. Put differently, once you log something as an MLflow model, the deployment options all work consistently, no matter what ML framework you choose. The tracking component tracks these models as part of runs and experiments, alongside their metrics, parameters, and other artifacts. And it also provides several visualizations of those metrics that I'm going to show you later. And finally, the model registry is a central hub to version these models, track their lifecycle, hand them off between different stakeholders, and share models in an organization. So let me walk you through a common lifecycle of a machine learning model in MLflow. As mentioned, the model format allows you to log any machine learning model that you've trained, and we log those models in different flavors. On the left side, you see some of those most popular machine learning models that we support. And we log those machine learning models, first of all, in a native flavor for each one of these frameworks. So to give you one example, if you use TensorFlow, we would just log the saved model format. And then we also log additional flavors, and one of them is called the Python function flavor, which exposes all of these models consistently as a Python function, which makes deployment easier. So if you log these models to an MLflow tracking server, they're logged as parts of runs in an experiment alongside their parameters, metrics, and other artifacts. Once you find a model that you want to deploy, you can add it to the model registry. And for the model registry, I like to highlight three things. The first one is versioning. When you refresh the same model with new data or update the model with different hyperparameters, you can add new versions of that same model to the model registry. Second, each one of those versions goes through its own deployment stage. So a newer version can be in staging, while a previous version is currently marked production. And third, in many teams, there's a handoff between data scientists who build these models and engineers who deploy them. And the model registry facilitates that handoff with a workflow to request and approve these stage transitions. And once a model is deployed, the MLflow model format supports many common deployment patterns, such as building a Docker container from a model, deploying models as Spark, batch, or streaming jobs, or deploying them to cloud inference services. So in order to make it really simple to get started with MLflow, we're adding auto-logging capabilities for the most common workflows. We currently provide auto-logging APIs for Keras, TensorFlow, and we've also gotten several contributions for others. And as you can see, with just one line of code, you get all of the model's parameters and metrics that are captured during its training run, and also, of course, the model artifact itself. So now that we've discussed MLflow as the foundation for MLOps, let's discuss how each step in the development lifecycle integrates with MLflow to provide an integrated end-to-end platform. So Databricks Notebooks are quite unique in that they actually provide you a multi-language development environment, which is important to really enable a unified platform for data engineers, data scientists, and data analysts. More specifically, you could write Scala code to ETL your data, SQL to analyze it, and Python to train a model, all within the same notebook. And of course, Databricks Notebooks provide several additional benefits, but in this talk, I'm just going to highlight a few that are particularly important for MLOps challenges. So one of the most important benefits of these notebooks is that they facilitate collaboration. Features like co-presence and co-editing allow multiple developers to work on the same notebook side by side and see each other's work. And of course, we also version notebooks and highlight which developer made which changes so that you can revert back if needed. And there's also a commenting feature with which you can leave comments for your colleagues so that they can collaborate with you asynchronously. And in terms of integration with MLflow, one of the key challenges for data scientists is to track their experiments and results and make them reproducible. So Databricks Notebooks have this run sidebar that shows you the runs that have been recorded in MLflow, and each run shows you its parameters and metrics, and you can easily find the best model just by sorting by the metric. Also, because each one of these runs is linked to the revision history of the notebook, all you have to do is click on the run and it takes you to the exact version of the code that produced that run and that model. So now that we've discussed MLflow as the foundation for MLOps and Databricks Notebooks, let's discuss the data science and ML workflow from the very beginning with the data. Delta Lake is a product developed by Databricks that we open sourced and contributed to the Linux Foundation last year. It allows you to make your data available in high quality and performance for downstream data science, machine learning, and analyst use cases. You can ingest data from any data source into Delta Lake, and I sometimes even ingest CSV files into Delta Lake to take advantages of its benefits. And I'll show you on the next slide how easy that is. And the Delta Lake itself is just a layer on top of your existing data lake so that the data is actually stored there, and Delta Lake just provides you with transaction guarantees and other benefits on top of this. So within Delta, you can transform your data from raw input into a data catalog and tables that represent the features that are used in downstream use cases. And I like to highlight two benefits of Delta Lake specifically for data science and machine learning. Number one is for training machine learning models using the machine learning runtime, which I'll discuss later. Delta Lake provides optimized read and write performance as well as schema enforcement. And that really helps you to allow that you always train on high quality data. And then secondly, for governance, we'll actually see on a later slide that MLflow is integrated with Data Lake, so you can easily track which data was used in an experiment and in a run. So this is just a very quick example to show you how easy it is to leverage Delta Lake even for data that you have lying around in CSVs. And you can read those into a Delta Lake table and take benefits of its features. One of those benefits is what we call time travel. Delta Lake keeps this write-ahead log, which provides you with the ability to look at your data at a specific version. So in this example, you can see that there are 7 versions of your data based on transactions that happened. And you can see who made those transactions and get details on exactly what happened. So if you want to access a previous version of your data, it's as easy as just referencing that version number. That's why we call this feature time travel, because you can really go back to the exact version of your data at the previous point in time. And one example for why you would want to do this is to reproduce a machine learning model that was trained on a specific version of your data. Again, to make this easier, we also created an auto-logging feature for Delta Lake. More specifically, this actually works for any Spark data source. So with a single line of code, in this case mlflow.spark.autolog, we keep track of each Spark data source that you access during a run, and the log itself will give you information about which table you've accessed. And if you use Delta Lake, we also tell you which version you used. So once your data is in Delta Lake, it's very easy to train machine learning models on top of it. On Databricks, we provide a pre-configured environment called the machine learning runtime. The machine learning runtime provides several benefits specifically for the MLOps lifecycle. The most important one is that we package up the most popular machine learning frameworks such as TensorFlow and PyTorch. And in some cases, we even add performance improvements to those libraries. On top of that, we provide libraries for distributing those workloads. So we integrate Horovod into the machine learning runtime to make it easy to actually distribute your machine learning training. And we also build in tools for hyperparameter tuning and AutoML to make it easy to optimize the performance of your models. So you'll see on a later slide how this actually also integrates with MLflow. And last but not least, environment management is one of the key challenges in MLOps. So we started using Conda to more easily let you customize your environment. So you can easily install libraries from within a notebook and also use environment specifications such as a conda.yaml to install all of the dependencies that you need. As mentioned, we integrate hyperparameter tuning with MLflow. So in this case, you can see that we use hyperopt, and it's as easy as configuring the search space and calling this API. And then to keep track of these hyperparameter search trials, we automatically log them to MLflow. So here you can see a visualization that is called a parallel coordinates plot. Each line here is a trial, and we color code them by the result metric, which in this case is loss. So you can easily pick the models with the lowest loss and inspect which parameter combinations actually led to good outcomes. Finally, once you know which model you want to deploy, the MLflow model registry helps you manage the deployment lifecycle and provides you all of the deployment options mentioned earlier. And just to give you one example, here you can see how easy it is to request a model from the model registry and apply it as a Spark UDF. So this will return the model version that is currently marked production for the model called forecast. So in summary, Databricks really accelerates the full machine learning lifecycle with MLflow as a foundation. I haven't made this explicit in this talk, but this platform is actually used by thousands of enterprises daily. And we even have customers that train hundreds of thousands of models on Databricks and manage their lifecycle with MLflow. So that's actually an example of a predictive maintenance use case where the customer actually trains a single model for each one of the devices that they have. But you'll also hear about other real-life use cases later from our customers. But before that, Sean Owen will actually give you a demo of what this full ML lifecycle looks like in the product.